Hello everyone, welcome to my YouTube channel. Today we will see strain energy. In this video, we will see major engineering applications is based on this particular principle, that is a strain energy. Now, in first chapter, we have learned a stress strain. In that case, we have used one metallic specimen, and that specimen we have on that specimen we have applied load. That load was gradually increases, and due to that, if you observe stress strain, it is get changed. If I consider the ductile material, in that case I can draw the stress strain diagram. So if I consider stress and strain along x-axis and stress along y-axis, then we observe stress strain curve. It is like this. Clear? So somehow it looks like this. Clear? The load applied was gradual. Load was there. Now if I consider up to the elastic limit, now let's say this is the first point. If I consider this point is E point, now when you release the load at this particular point, then as we know that the entire body will regain its original shape and size. However, if you consider when you stress any material, means you are applying some external work done on this particular object. So definitely energy neither created nor destroyed, it will transfer from one form to the another form. It's a simple principle. So if you observe this principle, then we will get to know that when you applied some external load or external work done on this particular specimen, then definitely there will be some kind of energy, some energy will be there. It is get stored within this particular body. Are you getting my point? What I'm saying? When we apply some force, which means there is some kind of work done is going to be happen on this particular body, and when this body is released, then we will get to know that that will is nothing but some energy, and that energy is called as a strain energy. Now I will take simple example. So you know the bow and arrow. So let's consider this is an arrow. Clear? So here there will be a string. Now when you stress this bow in this direction, which means external energy we have applied on this particular bow and arrow. Once you release this energy, then definitely this arrow will displace in this direction. Whatever the work done you are applying on this bow and arrow, it will get into this effect. So this work done is applied on the bow, and it will store in form of strain energy. Simple. So strain energy is nothing but which is absorbed within the body due to the straining effect, and that is known as a straining energy. It may be due to suddenly applied load, it may be due to gradually applied load, or it may be due to the impact loading. So in first year you might have learned the forging machine. In forging machine we apply some load from some height, that is nothing but it's a impact load. Clear? So first we will see some of the definition which is related to the our strain energy. So I will delete this. So this is along the E. Now first definition is about the resilience. What is resilience? The total energy stored in a body, commonly known as a strain energy. So if you observe this entire area under the curve, because this is nothing but is an total energy absorbed by particular specimen. I think no need to draw the diagram, so I just simply explain you. So this diagram can be obtained by applying the load at the two end on the UTM, and then we will get the this particular diagram. Clear? So when you apply any kind of load, then the body will get change its shape. Work done is applied on the specimen, so that work done is get stored in within the body, and due to the stretching, whatever amount of energy is get stored, that energy is called as a strain energy. Now that total energy up to the failure, before the failure, if you observe, entire this curve is known as a area. Within that curve we can consider the resilience. Now next definition related to the strain energy is nothing but it's a proof resilience. Proof resilience. Now when you apply the load on elastic material, or we can say ductile material, in that case if you observe up to the elastic limit, what happens up to this elastic limit, when you remove the force, then the body will regain its original shape and size. Up to that elastic limit point, whatever the stored energy is there, that stored energy or that region, we can call it as a proof resilience. So resilience is nothing but it's up to the failure. Before that point, whatever the energy is stored within that body is known as a resilience, and up to the elastic limit only, whatever the energy is stored within that body is known as a proof resilience. Clear? So next definition is related to the modulus of resilience. Now this modulus of resilience is nothing but proof resilience divided by volume of the body. It is just a simple ratio of proof resilience divided by volume of the body. So as we already discussed earlier, that strain energy may be due to suddenly applied load, it may be due to the gradually applied load, or it may be due to the impact load. So I will derive expression. So let's see the expression for strain energy. Expression for strain energy stored in body, stored in body when the load is applied gradually. Clear? So there are different three types of load we are going to see over here: gradually applied load, suddenly applied load, and impact load. So first we will see the gradually applied load. So if you want to observe the diagram, then I can draw like this. If I consider the force and delta L, or elongation we can say, then I can say that when you apply the load gradually, so it is gradually it will increase, and as you know, the force applied on the body, it is get increase along with the change in length, it will increase. Clear? So I will draw the curve like this, straight line will be there, simple. And if I take this, then I can say this is an area where we are interested. So let's say this displacement is x and the applied load is P. Simple. Now, what is strain energy? Strain energy stored within the body is equal to the work done. So I can write strain energy that will be equal to the work done. Simple. Now, first, if you want strain energy, then you must find out the work done by the load. So first I will evaluate work done by the load. So area under the curve. So from this I can easily say that it's a triangle. So you need to evaluate the area for the triangle. So that is nothing but it's a half BH, B into H. Simple. So let's say this is an work done by the load. Let's say that is equation number 1. Now what is this X? X is nothing but it's a change in dimension, or we can say change in length. So that can be evaluated from this formula, that is strain equal to the change in length divided by original length. So I can write change in dimension divided by original length. So this is simple formula. So what we need change in dimension, so strain into length. So I can write X equal to strain, that is E into length. So this E I can write stress divided by strain, that is equal to modulus of elasticity, is nothing but stress divided by strain. What I want strain. So strain, that will be equal to stress divided by modulus of elasticity. Simple. So instead of E, I will write sigma by E into L. Simple. So I will write this is equation number 2. Next is just put the value of this X in the W. On, we can write stress equal to force divided by area. So I can write P divided by A. So in for P, I will get stress into area. Now we know the P and we know the value of X. Value of X is sigma by E into L. Clear? Just put this all in equation number 1. So I can write from equation 1, work done, it will be equal to 1 upon half, instead of X I will write sigma by E into L into sigma into A. So instead of P I am writing sigma into A. So that work done will be equal to 1 upon half sigma and sigma, it will be sigma square into A into L divided by E. Now what is A into L? It's nothing but a volume. So I can write work done equal to half sigma square V divided by E. Clear? So we got the formula for work done, that is equal to sigma square divided by 2E into volume. Simple. So as we know the work done equal to the strain energy, so I can write strain energy stored in the body, that will be equal to sigma square divided by 2 into V. Simple. Now as we have seen some definition earlier, so this will be nothing but resilience. Now if you want proof resilience, then I must write sigma square divided by 2. Now instead of E I must write, sorry, the sigma I can change. Now this is nothing but it's a total stress. Clear? But what is proof resilience? That is amount of energy stored within that elastic limit only. So this is constant. Sigma, sorry, modulus of elasticity is constant, and volume will remains also constant. Only the change will be is nothing but it is related to the sigma. That is stress at or up to the elastic point. Clear? So I can write this sigma star, that will be equal to stress at elastic limit, stressed at elastic limit. Simple. So this is what a proof resilience. If I write for modulus of resilience, then it is simply proof resilience divided by volume. So this volume and volume it get cancelled. So I can write sigma square star square divided by 2e. So generally we consider this sigma star, that is nothing but stress up to the elastic limit only. Simple. I hope you understand the concept of strain energy when load is applied gradually. Clear? So we will see the second expression for the strain energy, that is expression for strain energy in the body when load applied suddenly. Clear? So when there is sudden load is applied, in that case what will happen, we will see in the graph. So if I draw the force and displacement diagram, then there will be a force, and due to that force sudden elongation will be there. So this is nothing but force and this is nothing but elongation. So we are not applying gradually force, we are applying sudden load. So definitely this will become an area. Clear? So let's start the same derivation. First what we need to find out the work done, then we will put the value of force and elongation in terms of sigma and e, and then we will get the expression. Clear? So remember, when the load is applied suddenly, now here if you observe, this is an bar, and if you apply sudden load, so let's say this is fixed one, and suddenly if you applied the load, clear? Are you getting my point? What I'm saying, you are applying suddenly 100 kilonewton on this load. What will happen once you apply the load? At that moment this body will get elongated. Elongation may be x. Clear? Due to that sudden load, body will get deformed. Simple. And from that we need to evaluate work done by the load. So I will write work done by load, that is nothing but p into x. So area under this curve. Simple. So instead of p, what I will write, sigma into a, and instead of x I will write sigma by e into l. So same thing I am repeating over here. So here this expression will be sigma square divided by e into al. So instead of al I will write again v. Clear? Now if you compare this equation with the, so this is nothing but so work done by load, or we can say it's an strain energy when load is applied sudden. Clear? So what we need, when you compare this equation with this equation, wait, I will show you this equation with this equation. This equation. Clear? So I can rewrite this equation again, that is sigma square divided by 2e, or we can say wait, now here we want in terms of p and a. So I will rewrite the expression, that is work done by sudden load, that can be written as p into x. So I will keep that p remain same, into instead of x I will write stress divided by e into l. Clear? Now previously we know the expression we have derived for that, uh, gradually increase the load, that is sigma square divided by 2 into v. If you compare these two equations, then I can say that sigma will be equal to, so if you compare with this sigma square 2e into v, then this sigma and this sigma is get cancelled, then I can rewrite 2p divided by area. Simple. So this volume I can write in terms of area into L. So this L and this L will get cancelled. Simple. And this E and this E will get cancelled. 2 will go in that side. A will go in this side. So I will get sigma is equal to 2p divided by A. So from this case, it is clear that the maximum stress induced in the body, is when you compare with the sudden applied load and gradually applied load, then definitely stress induced, I will write stress induced due to suddenly applied load is twice the stress induced when the same load is applied gradually. Simple. So if you consider the gradually applied load, then stress is nothing but force divided by area, that is we have considered earlier. Clear. Now here if you observe, the stress is equal to 2p divided by area. Is that clear to everyone? So definitely it's a twice which we have earlier applied. Now there is a last expression we want to see when there is an impact load is there. Clear. So I will rewrite the third condition, that is expression for strain energy in the body when the load is applied with impact. Clear. So let the load is dropped from some height, then what will happen? So for that purpose I will need to draw one diagram. Clear. So let's say there is an one bar is there, it is hang at this position. I hope this is visible to everyone. Let's say this is an one bar, the bar is having one collar over here. Clear. Now there is an load we are considering over here, so load is attached over here. Now there is a difference between impact and suddenly applied load. In suddenly applied load, if you observe, there was no height. Clear. So this was the case, or in this expression if I consider vertical bar, then I can say if this is an bar is there and at this end we applied suddenly load. However, if you observe, there is one load is there, this bar is there and this bar is having some color. Now when you apply this load from some height, what will happen? That is nothing but it's an impact, and due to that impact this body will get deformed. Clear. So deformation of the rod may be this one. Try to understand. This will be the deformation of the body. Now if I consider the length of rod is this much, and if you see the deformation of the body, so I can say this is delta L. Clear. Now when you apply the load from some height, clear, so this is nothing but it's an load. Clear. So this is nothing but a collar. When you apply this load from some height, that is h, and when there is an impact load is there, clear, due to that this body will get deformed. Simple. So for that purpose, let's see the derivation. Again we will see the strain. The strain in the bar is given by, that is delta L divided by L, and that will be equal to sigma by E. So strain equal to sigma by E, and strain is also known as change in length divided by original length. So let's say that is expression A. Clear. Now what we want? We want work done. So first find out work done by the load. So definitely it will be equal to P into H plus delta L. Clear. So let's say this is an expression 1. So how much work done will be there? Whatever the load is there, so I can say P, then it is get multiplied with the H and delta L. Clear. Now strain energy stored in the rod. Clear. So this will I can write, that is U equal to sigma square divided by 2E into V, or we can rewrite, instead of V I will write A into L. Clear. So this is expression number second. So I can say that this strain energy, that is equal to the work done. Clear. So from equation 1 and 2 I can rewrite sigma square 2E into A into L, that is equal to the force P into H plus delta L. Now instead of delta L I will rewrite this equation. I will take this in this side, P into H plus, instead of delta L what we will learn, that is sigma by E into L. Clear. So it will remain same, sigma square divided by 2E into A into L. So I will multiply the bracket, so P into H, then P into sigma divided by E into L equal to sigma square divided by 2E into A into L. Clear. Now I need expression, so what I will do, I will multiply by 2E divided by AL to both sides. Clear. So I will get one expression. So if you multiply 2E divided by AL, means 2E AL, it will get cancelled, it will remains only sigma square. So here the equation will be become 2PEH divided by AL plus, I can rewrite 2P sigma into A. This L and this L will get cancelled, equal to sigma square. Simple. Now if you take expression the sigma square in this side, then I can write sigma square minus, so when you consider in that side it will get minus 2P sigma divided by A minus 2PEH divided by AL equal to 0. Clear. So this is an expression where we will can solve this equation by using this formula, that is root we can evaluate, it will be equal to minus b plus or minus under root of b square plus 4ac divided by 2a. Value of a is 1 over here, value of b, so I will write root, so I can write sigma equal to 2p divided by a, so that is b, it's minus 2p, but here minus is there, so I will write positive 2p plus or minus under root of 2p divided by A whole square, that is B square. It's minus, but if you consider the square, then it will become positive. So I am writing positive plus 4. Value of A is 1. So 4A into 2PEH divided by AL. Simple. It's not over, divided by 2A. 2 into 1. Clear? So sigma will be equal to, so if you divide by the 2, then I can write, so this 2 and this 2 is get cancelled, so it will become P by A plus or minus under root of, so we are taking these 2 in under root, so I must take 4, so this will become 4p square divided by these 2. If you take in under root, then I must write 4a plus 4 into 2 PEH divided by, so these 2 I'm taking in under root, so I must write 4 into A into L. So this 4 4 4 4 it will get cancelled, so I will get sigma equal to P by A plus or minus under root of P by A. So this is square, this will be square, so I will write P by A square plus 2PEH divided by AL. Here if you observe, there is a P by A. So if you consider the positive, then I can write P by A plus under root of P by A square 2PEH divided by AL. Clear? Now I will take P by A outside, so I will write P by A plus, I will neglect the negative sign, so I will just consider the positive only. P by A, here I can write 1 plus, so I am taking P by A outside, so here I will get only 1. 2PEH divided by AL into, I must write down here A square divided by P square. Clear? So this P and this P it will get cancelled, this A and this A it will get cancelled, so I will get sigma equal to P by A plus P by A under root of 1 plus 2 AEH divided by PL. Again, if I consider P by A common, then I can write P by A in bracket, so here I will get 1 plus under root of 1 plus 2 AEH divided by PL. Clear? So this will be the expression for the stress. Find out when we apply the load, and the load is nothing but an impact load. Simple. Now if you consider this equation, from this equation I can conclude, or I will write down some important conclusions over there. So first conclusion is, if delta is delta L is very small, means what, if there is a small deflection is there, comparison with H, if there is a small deflection is there but the height is very high, so in that case we can neglect that delta L, so we can neglect delta L. Then how the work done will be there, definitely work done will be equal to P into H, there will be no delta L. Clear? So that will be equal to sigma square divided by 2E, that is strain energy, into AL. Clear? So sigma square, that will be equal to 2E, just multiply in this side, 2E into PH divided by AL. And if I take the value for sigma, then I can write this will be under root of 2 EPH divided by AL. Simple. So this will be the expression for the sigma when there is a negligible deflection of the rod as compared to the height. Now next conclusion is, if I consider the H value is negligible, so we are applying the load at the end only. If you apply the load at end only, then if you put H value in this equation, so this equation will become, so I will rewrite that equation, sigma it will be equal to P by A 1 plus under root of 1 plus, so here in expression if you observe there is an H, if you multiply by 0 with any, then it will become 0. So I can write P by A 1 plus root of 1 is 1, so I can write 2P divided by A. Clear? Now if you recall the equation, that is sigma equal to 2P divided by A, so this equation we got when load is applied, suddenly applied load. Are you getting my point? So right now you might have learned or you might have observed that this sigma value is get when there is a sudden applied load. So there is difference between sudden applied load and impact load, that in impact load we apply load at some height, and if you make that height equal to 0, then it will become a sudden applied load, and definitely we will get the same expression which we have seen earlier. Clear? So in today's lecture we seen strain energy, proof resilience, modulus of resilience, resilience. Then there are different three cases are there of strain energies when the load is applied gradually, suddenly, and impact. I hope you like the video. Thank you.